We have been scouring the heavens for centuries, hoping for signs of life. And one planet above all has been the object of our obsession. The red planet Mars. The first explorers to set foot there will carry on the search, but they will face a deadly threat. Because what we have already found on Mars is not alien life, but alien weather. Mars is consumed by dust storms, blasting its surface at 200 miles an hour. And now scientists are trying to calculate the risks for the astronauts who will go there. Wes Ward is the chief of Mars exploration for the United States Geological Survey. Ever since Mariner 9 became the first spacecraft to go into orbit around Mars, he has been driven by the dream of a manned mission to the Red Planet. But his weather forecast is danger.
When our first astronauts land on Mars, they're probably going to have a pretty tough time of it. The first time we really got to understand what's going on Mars was with the Mariner 9 mission in 1971. We'd flown by Mars 3 times in the earlier 60s, but didn't see very much. We get to Mars with Mariner 9, beautiful spacecraft, working perfectly, all their instruments are ready to go, and we turn our eyes to the planet to see what we can find out. And we look down, and we see absolutely nothing. The entire planet is covered by one global dust storm. Well, all the geologists were terribly disappointed because they wanted to see what the planet was doing. But the science fiction part of my mind says, oh yeah, these are these great dust storms that we always have read about. And isn't this cool? Here you have an entire planet that's covered by one massive storm, and something fantastic has to be going on Mars. Sooner or later, and I hope a lot sooner, I'd like to see it in my lifetime, it's possible to get to Mars 20, 30, 40 years. And of all the things we have thought about when we're going to see on Mars, the #1 problem we're going to have is weather.
In the Mojave Desert outside Los Angeles, a team of engineers prepares for a unique experiment. Using powerful fans, they plan to bring a Martian dust storm down to Earth so that Wes Ward can have the dubious honor of enduring Martian weather firsthand. Wes has a deadly serious scientific purpose, paving the way for future astronauts. On Mars, dust moving at high speed will place them in mortal danger. It's vital to know the effects Martian weather will have on both men and equipment. An astronaut's spacesuit is his life support system, his only protection from an alien environment. No one has entered this machine before. No one knows what Wes will experience until he steps inside.
When someone says to you, you're going to step inside a tornado machine, that gives you a reason to pause, I guess, early on. But I think most what we need to do is step out of the academic, allow something to happen, because very often that's how some of the best discoveries take place. You put yourself in a position to make observations, to make interactions. And if you're really lucky, not everything goes as predicted. There's that one other piece, that second piece, that third piece of something you never expected. You're on the way to discovery.
Matched up. Here, and it's ready to go.
Let's go to Mars.
Down!
But Wes discovers that earthly weather can also bite. Desert winds have reached 50 miles an hour, making the structure unsafe. Work is called off for the day. But on Mars, a storm like this would last for weeks. For Wes Ward, Mars is a vision of the Earth as a desert world, where the dust storm is king. When Mariner 9 reached Mars, it was a whole month before the massive dust storm finally died down to reveal a lifeless, desert world. Summer temperatures rarely reach freezing point, and they plummet by 10 degrees when dust storms block out the sun. With no water and no life, wind and dust are the major forces shaping the Martian surface. Dust storms rule the red planet, and now scientists want to know how these alien storms are born. At NASA's Ames Research Center in California, they go to incredible lengths to simulate Martian conditions. A wind tunnel is coated with ultrafine red dust. On Mars, millions of years of high winds have pounded the rock to a dust as fine as talcum powder. Scientists must wear breathing masks, but when the experiment begins, they have to leave altogether because the Martian air is 100 times thinner than the Earth's. The entire laboratory must be pumped out to create a virtually airless no man's land. There isn't enough air pressure left in the wind tunnel to force a single speck of dust off the ground, even with a 60-mile-an-hour wind. Scientists need another Martian laboratory, the deserts of the Earth. And Steve Metzger, a geologist from the University of Nevada, makes an amazing discovery. It takes more than just wind to blow up a storm.
This is kind of a general wind blow. It's picking up a lot of sand, and it's going to definitely cover a wide area, but it's only taking it up a few dozen yards. It's obviously able to carry a lot of stuff. There goes my water bottle. Oh wow, I can just really feel sand bouncing off every surface of my body. Sand is bouncing along and it's picking up dust because it's eroding it and splashing it off the surface.
Steve thinks sand is a key ingredient, and the Mars wind tunnel shows why. The bigger sand grains bouncing along the surface help to raise dust into the thin but fast-flowing air above it. The effect of sand is crucial in explaining how dust storms can happen in the thin Martian atmosphere. And the final evidence comes from Mars itself. The Mars Global Surveyor spacecraft captured these pictures of shifting sand dunes. And another powerful force seems to be at work. The same spacecraft has been detecting strange, fuzzy spots on the planet's surface, leaving long, dark trails. But there were no pictures from ground level until the Pathfinder mission touched down and Steve Metzger spotted something that NASA's own scientists had missed.
After the mission landed and I downloaded some pictures off the internet, used the right filtering and a little computer processing, you could see the strong column that's going straight up. It might go 1 or 2 miles up into the air, right against the horizon, showing up against a background of quite a bit of dust haze.
The tall, twisting columns are called dust devils. And our deserts are so similar to Mars that we have them too. Whenever dust storms happen on Mars, dust devils always seem to be present. They're also under suspicion on our own world. Because as dust storms rule Mars, they also roam the Earth. In the 1930s, the North American prairies were overrun by a plague of storms that lasted for months, and then years. The terrible hardships of the Dust Bowl days caused the biggest mass exodus of people that America has ever witnessed. In the long drought of 1983, Melbourne, Australia, was attacked by 2 million tons of dust in a creeping cloud 1,000 feet high. A desert storm in the heart of the city, trapping 3 million people on the choking streets. And in Southern California, a fast-moving wall of dust turned a busy highway into the worst traffic accident in American history. On the day after the Thanksgiving holiday in 1991, thousands of people were using California's Interstate 5. The surrounding farmlands are borderline desert, and this was the last of 6 years of drought, the worst on record. The soil in the fields had turned to dust, and on that day, the dust started to move. 164 cars and trucks disappeared in an all-consuming cloud of dust. None came out the other side. Officer Mike Brown, a helicopter pilot from the California Highway Patrol, was scrambled to the scene.
It seemed like a normal day. The weather here was clear. It was a little bit windy, but nothing out of the ordinary. When we got to the area of Interstate 5, most of the freeway was obscured from dust. It's just a complete wall. And so until we were approximately 50 feet above the ground, we couldn't see anything that was on the ground. It was completely obscured. The scene was almost surreal. You walk into this scene and you begin assessing damage. Vehicles are twisted, mangled, embedded in each other. It's like a battle scene, but it's in the middle of a dust storm.
150 people were injured in the dust storm that struck Interstate 5. 17 were killed.
I'm a native Californian. I've lived here for 53 years, all my life. I've flown in this particular area for 20 years. And to my knowledge, we've never had a phenomenon like this. The dust cloud went as high as 14,000 feet. And it was as if the dust were being generated from some type of a machine.
There seemed to be nothing different about the weather conditions on that day to trigger the Interstate 5 disaster. But Steve Metzger believes it's possible that dust devils may have played their part. Just as they helped to start global dust storms on Mars, sand can get dust off the ground, but Steve thinks that dust devils may finish the job.
Dust is actually very hard to move. In order for the wind to erode the surface, the wind has got to get down to the surface. And every surface has its characteristics as to how it drags the wind as it moves across that surface. We can see it by seeing how little wind is moving right across this surface, but the moment you get further up into the air column, the wind speed really starts to pick up and it gets to be pretty strong. This mast is measuring the wind speed at a whole bunch of different levels, and we can project down mathematically onto the surface to see how much energy is actually making it here. One of the ideas on how that is linked from the dust devil to the dust storm is that the dust devils are lifting up enough dust in a certain area to heat up the atmosphere, turn that atmosphere unstable, and really get some strong winds churning in it. Then those sweep down across the surface, raising huge quantities of dust and leading to the global dust storms. Oh, they're perfect. Look at that. There's a real clear column right yonder. There's sand ejector skirts on these guys because they're flipping out the heavier sand. It's perfect. It'll sandblast the car too. That'll be nice.
Steve also faces being sandblasted as he joins the chase for hard evidence.
All right. This dust devil is really wide. It's got several parts to it.
This is going to be nasty. Oh! 45 milligrams per cubic meter is kind of dusty. Oh, wow. It's hard to breathe inside those two. Another one, excellent column forming. All right, look at this. This is great. This is a perfect day. Dust devils are able to just take whatever they can erode off the surface, and it's an escalator ride up into the sky, way above the area that normal wind whips up dust. And this is a calm day. There's nothing else going on except a gentle breeze, maybe about 5 or 10 miles an hour. Two big dust devils working away. That's where they're happening. That's where we'll go.
Steve wants to measure how much dust is being lifted, but the sandblasting effect inside a dust devil gives him two problems: getting in and getting out. Lance comes to the rescue, Steve's name for a specially adapted truck. Its 20-foot pole carries the instruments and takes the sting out of dust devil work. It's 2 o'clock in the afternoon, exactly the same time that dust devils spring up on Mars.
Dust devils can happen anytime you have a dry surface being warmed by a sun on a clear sky.
Off we go.
The surface heats up, the air right above the surface gets warm. This air is unstable, it starts to rise, especially if a little wind comes through and gives it a bit of a twist. Are you all holding on tight? It's off and running. We've got a visible dust column, and the dust devil is started. It's trying to form up. It's about 50, 60 feet in diameter. Oh yeah, here it goes. It's slowly turning. Oh, all right, this is going to be good. All right, baby, here we go. Woohoo! All right. Dust devil number 1. Probably going up about half a mile. Oh wow, it is tough to get in front of this thing. It is moving fast. Here we come. Woohoo! Ow! Damn!
On Mars, dust devils like these can be 5 miles high and almost a half a mile wide. But even here on Earth, Steve finds that just a few can lift 9 tons of dust into the atmosphere in this small area alone. Over a wider region, that's enough to bring a monster storm to life.
The sun is beating on the dust, the air around the dust warms up. That can change the whole thermal dynamics of that section of the atmosphere. That can get regional currents going in the atmosphere, and that can lead to large-scale dust storms, both on Earth or on Mars.
Steve cannot yet predict dust storms, but he's beginning to understand their causes.
The dust storm that swept over I-5 may have started because dust devils upwind of it were feeding dust into the atmosphere, making that atmosphere unstable. And although it's also possible that a very strong wind pattern of a more conventional sense was responsible, dust devils can do that sort of thing, charging the atmosphere with dust, heating it up, and a regional dust storm results.
Once dust devils have set a storm in motion, no power on Earth or Mars can stop it. The Mojave Desert in California is scarred by the colossal blasting power of wind, dust, and sand. For 15,000 years, the wind has been grinding rock into these streamlined shapes called yardangs. But much larger Yardangs can be found on Mars. The Global Surveyor sent back these pictures. 300-foot-high monuments, sandblasted into shape for over 100,000 years. Martian Yardangs are carved by a maelstrom of dust and sand, moving at up to 200 miles an hour. Geologists like Wes Ward have seen what wind can do to solid rock. But he's about to find out what it could do to astronauts.
Once you get on Mars, if you're very unlucky, you might encounter some of these dust devils and Martian windstorms. And what that's going to do for us is start to move around some of this very fine sand and loose, fine Martian dust. So it could affect the operation of your suit, it could affect the operation of your rover, it could affect the habitat. Dust is going to very easily get into the airlock and inside the habitat, so we could start to face some biological considerations very quickly. But I think most off, I would be concerned about the wind simply blowing out there.
Dawn is the calmest period of the desert day. But Wes Ward's team of engineers have only a narrow window of opportunity before the landscape warms and the winds pick up again. The effects on a man of fast-moving dust and sand cannot be predicted. In the final tense minutes before sunrise, Wes ponders the possibilities. But the wind may be the least of his problems. A buildup of static electricity in the tornado of dust could easily disable his equipment. On Mars, this would leave an astronaut helpless.
Ho, ho!
Like the first astronauts on the moon, Wes will make a live transmission.
Wow, is that big? Is that stable? My goodness. The ground is soft. Beneath my feet, I can't see my feet anymore. There is a great deal of dust swirling around me. I'd pick up sand grains and feel them. See how those sand grains interact with the Martian atmosphere. Picking up some of the sand and watching it go through my fingers. Maybe tossing some up in the air just to see how far it's going to go. And this is a device.
First contact, and Wes is still able to stand upright and function normally. He tries an electronic wind measurement.
And there's a pretty good gust in through there.
Things are about to change.
650. 60 miles an hour pretty easily. Perhaps the winds are now strong enough that I can start to feel the torque on my arm and on the backpack. Looks like I'm in charge of static electricity. I can feel it in both hands. My goodness.
Static is building in the blizzard of fast-moving particles. The dust is sticking to his visor and instruments.
Yeah, it's pretty close to zero. Vibrating around, rotating around. I can hardly see now. I can hardly see.
After just 10 minutes, the sand, dust, and static electricity take their toll. Wes is working blind. His visibility is gone. His wind gauge and a helmet camera have both failed.
Power's off. This activity, this experiment, is just one of a number of small steps that we'll take that I hope the crews that get to Mars find exceptionally useful, teaching the astronauts what could happen to them and what they should be looking for. The thing that really surprised me was the encounter with static electricity. And actually became a little bit concerned about it. Would that mean that, for instance, I was picking up a charge and all the instruments, and if I came in contact with anybody else, would I give them something they weren't quite prepared for?
In the freezing, airless deserts of Mars, spacesuit malfunction would mean certain death. Wes's discovery is a vital step on the road to the Red Planet.
So for me, and for everybody that I worked with, this was really new information. No one had really expected all of these things. So this will go in the ledger as the first set of observations of this kind.
The first actual footstep on the surface of Mars may be only a generation away. But for now, only Wes Ward has had a taste of weather on a Martian scale. And only he can imagine a dust storm that grows from nothing to cast its shadow over an entire planet. His vision of the Earth as a desert world becomes reality.
Now we have dust storms on Earth too, but because of vegetation and water, the wind is really held in check. Let's imagine that the Earth is a little different now. Perhaps we don't have any vegetation, perhaps we don't have any water. Let's take one of those Martian-sized dust storms and bring it right down to home. A Mars day is just about the same length as an Earth day. And about 2 o'clock in the afternoon, when the sun has been beating down all morning, the ground is as hot as it's going to get that day. That's the time for Martian dust storms to spring up. A Martian dust storm might begin very simply. Maybe it's just a dust devil or two somewhere around the house. We might see a dust devil in the order of a few feet high start to grow. Spins a little bit faster and faster. On Earth, dust devils are really something of an amusement. But on a planet like Mars, dust devils are perhaps the dominant destructive force. Other dust devils come around, perhaps they're starting to coalesce. And what they are doing are starting to build into one giant dust storm. They're now growing up to the size of the house and maybe the trees. These are the first guard, the first wave of a big and deadly storm coming.
Dust devils are filling the air around the house. But this is no hiding place. Martian dust is as fine as talcum powder. It will creep into the house through any gap it can find. And it will soon be impossible to breathe. Dust devils stretch to the horizon in every direction. The approaching wind will sweep up the dust, creating a wave 5 miles high, sandblasting everything in its path. The storm is now moving at well over 100 miles an hour, and there is nowhere to run.
Oh, I don't like this.
This is just the beginning. A dust storm on a Martian scale would grow to cover the Earth. Humans will face these monstrous storms when Wes Ward's dream is realized, and astronauts travel to Mars. But the dust storms that roam the deserts of the Earth are held in check by our thick atmosphere, and 2/3 of our planet is covered by ocean. The Earth will never turn to dust. But there is another storm, far more violent than anything that can be found on our near neighbors in the solar system. Weather far more extreme than the Earth's, or the mighty dust storms of Mars. The outer solar system, realm of the giant gas planets, is the true home of the superstorm. The planet Jupiter is so vast that more than 1,000 Earths could fit easily inside. A planet that's all atmosphere. As long ago as the 17th century, the astronomer Cassini saw a mysterious dark shape moving on Jupiter's surface. The Great Red Spot turned out to be a type of hurricane, twice the size of the Earth. Now, after more than 300 years, the Great Red Spot is still raging, and it's not alone. The surface of Jupiter is teeming with storms. Weather on Earth is powered by the sun's heat, but Jupiter only gets a fraction of this energy because it is 5 times further from the sun than we are. Jupiter's weather is driven by a powerful engine deep in its secret interior. The greatest flashes of lightning ever seen were detected on Jupiter by the Galileo spacecraft. Thunderbolts 50 miles across and 100 times brighter than typical lightning flashes on Earth. Only Jupiter's outer surface is visible, but its lightning gave us a window into the planet's hidden interior. And when 700 miles of cloud broke its surface, planetary scientists were seeing the same thunderstorms as those on Earth, but on a terrifying scale.
And this was extremely exciting because now we had lightning on another planet, and we've actually correlated the lightning with certain types of clouds that you see on Jupiter. In particular, these beautiful bright white plumes that come out of nowhere and just erupt in the low pressure regions on Jupiter.
Jupiter gives out twice as much energy as it receives from the sun, with heat left over from the planet's formation. As it cools, hot gases rise towards the surface, powering thunderstorms as they go. These are the thunderstorms on Earth, seen from space. Tim Dowling wants to know what Jupiter's thunderstorms look like from the inside, but he only has sparks of light to guide him.
Of course, when we do planetary science, we're always looking down, and when you're a terrestrial meteorologist, you get to look up where you actually get to fly through. We have a lot of limitations. We have this great existence of lightning. We know some other things about it, but we can't get inside the thunderstorm on Jupiter, and that is killing us.
Tim is a professor at the University of Louisville. For the past 5 years, he's been analyzing data from the only spacecraft to attempt the perilous descent through Jupiter's atmosphere.
3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
In 1989, Galileo was launched on a mission to study Jupiter and its moons. After a 6-year odyssey, it was in a position to drop a probe through Jupiter's clouds.
We were able, because it was an orbiter instead of a flyby mission, to plan very carefully a sequence of experiments or observations where we could look for lightning, and we knew pretty much where to look. We want to look in the low pressure rather than high pressure, in the low pressure zones on Jupiter.
Low pressure means thunderstorms, and the probe went in at 106,000 miles an hour. The probe headed for the center of the planet. It fell for 57 minutes, but to Tim Dowling's dismay, it detected almost no water. And with no water, there was no sign of thunderstorms. By sheer bad luck, it had hit one of the driest regions on the planet. 97 miles down, radio contact with Galileo was lost, and the probe was gone forever.
Just one sample of this enormous planet, it's tantalizing, but it raises more questions than it answers.
Tim hadn't found his thunderstorms on Jupiter, so his quest to understand them shifted to the Earth.
We're here inside the atmosphere of Earth, of course, and looking up. So you can get a great deal of information about the storms, the mechanisms for thunderstorms and lightning by doing very careful measurements of Earth's atmosphere and then try to carry that over to Jupiter.
Those measurements are about to be made. At the height of the summer storm season, over 100 weather scientists have converged on the Kansas prairies for the biggest study of thunderstorms ever held. They're hunting for supercells, the most dangerous thunderstorms on Earth. Planetary scientists like Tim Dowling believe that giant versions of these storms are producing the lightning flashes beneath Jupiter's surface. The hot afternoon sun is evaporating moisture from the land, creating tall columns of rising cloud. Thunderstorms in the making.
And I'm sort of thinking that you guys might want to head down that way.
The Earth experts want to understand how storms build. In order to predict them, they need a three-dimensional portrait of a storm. But they have to catch one first, and they have a Jupiter expert on their tail.
They've got storms here, 10 o'clock, 2 o'clock, all the way across the horizon, and they're going to have to make some choices. It's going to be really cool to see how they decide where to go to put the first balloon up.
Command Post radar shows that one of the storms they're tracking could become a supercell. Ground teams race to head off the moving target, and Command brings out its secret weapon. The heavily armored T-28 military aircraft is scrambled to fly directly into the heart of the storm. Its mission is to measure the strength of lightning inside the supercell, something that can only be done from the air. It sounds like madness, but this is the only aircraft in the world that's licensed to do it. Tim Dowling hopes that by establishing a relationship between lightning intensity and the size and growth rate of the Kansas storm, he'll be able to do the same for Jupiter.
What we need is a fairly robust or very good model of lightning and thunder. If you have a model that does a good job of predicting or describing Earth's weather and Jupiter's weather at the same time, then you feel much more confident about the underlying physics and your understanding.
Ground forces launch a balloon into the storm to measure how fast and how high the thundercloud is rising. Above them, the T-28 approaches the most dangerous part of its mission. The massive updrafts of the storm threaten to tear the plane's wings off in a process known as wind shear. The same forces create lightning when water droplets freeze into ice particles at high altitudes. As they rise inside the storm cloud, they rub against each other, creating massive charges of static electricity. Eventually, enough charge builds up to explode as lightning.
And it's getting pretty dark. I don't know what's coming next. And lightning.
Very close. Lightning, lightning. Lightning, lightning.
The thunderstorm is now 10 miles high, the maximum possible before it hits turbulence in the atmosphere and flattens out. This is an enormous storm. Suddenly, a tornado touches down on the horizon, the supercell's frightening calling card. The second balloon launch has to be fast. Just a few miles away, the twister is already causing havoc. And now it's heading their way. The T-28 has detected so-called super bolts in today's storm. On hot summer days, the atmosphere expands, and thunderstorms can climb much higher than normal. This one went to a height of 10 miles, with updrafts of 100 miles an hour. Tim Dowling has seen that the more room a thunderstorm has, and the faster it grows, the bigger the lightning it produces. And in his imagination, he descends into the colossal thunderstorms to the west of the Great Red Spot.
See this incredible eruption, almost an atom bomb that's going off. And it's the size of Alaska, this thing. So it's just going to be like a wall, an enormous wall that goes up. And instead of going up 10 miles or so, we're talking 30 miles and just towering up overhead.
Now Tim wants to compare Jupiter's lightning with Earth's. No one knows lightning like a T-28 pilot.
This thing can get hit by lightning.
Yes, in fact, we've...
Charlie Summers shows him the damage.
Strikes that have hit the aircraft.
What does that look like? Can we see?
Yeah, let's take a look back here. Usually the lightning, when it strikes the aircraft, doesn't leave any damage, but usually we get an exit. Like,
oh, interesting.
This is an exit where the lightning actually came out. Now, it's not that even when it happens, but I usually smooth them out a little bit just...
So that's like a thumb's width, that's a typical size?
Yeah, and that's a pretty heavy lightning bolt that is burned as it comes out. And the aircraft's been hit...
Oh yeah, there's chips all down here.
Yeah, and then there's bigger ones here.
The average commercial airliner is hit by lightning once every year. There's no armor plating like a T-28, but they're designed to take 10 times the jolt packed by a typical thunderbolt on Earth. But could they withstand a thunderstorm on the planet Jupiter? And lightning bolts that deliver the electric power of a large industrial city in a single heavyweight punch.
One thing, of course, I'll never get to do is fly in an airplane through Jupiter's cloud, but I would just love to look out the window, just like you do flying in the window seat of any airplane. And the question is, what would it be like if you were actually there?
Let me just put that up for you. There you go.
Ladies and gentlemen, for those of you who are awake, there's some pretty spectacular storm activity out on the right-hand side of the plane. Although it's some distance from us, we could be experiencing some turbulence ahead, so I'm going to go ahead and put the seatbelt sign on for a while.
If you actually flew in the vicinity of one of these enormous thunderstorms, you might see more than you want to see. If you actually go up to the cockpit, then you can get this incredible panorama of what's above, below, and to the side of you.
Our Alpha.
The scope is so huge, it would fill your peripheral vision, and you might wonder what the heck you're doing there. Of course, if you're looking at a tiger behind bars, it's a beautiful, magnificent animal, but if you actually climb into the cage, that's a very stupid thing to do. The actual energy that's contained in one of these enormous discharges, lightning strokes on Jupiter, is over 100 times more than the typical lightning stroke on Earth.
But lightning isn't the only problem. On Jupiter, the updrafts reach 200 miles an hour, twice as fast as the biggest thunderstorms on Earth. Jovian thunderstorms are driven by enormous energy, boiling up from the center of the planet. A superbolt on Earth causes a pinprick in the T-28. But Jupiter's lightning could blast a hole in the fuselage.
Although it might be a great honor to be on Jovian Airlines 101, it would also be probably your last flight on Jupiter.
But these nightmare thunderstorms are small fry, providing energy for something far more terrifying. Energy to feed a storm twice the size of the Earth. Energy that's kept it churning for more than 300 years. Energy that powers the Great Red Spot. Jupiter's Great Red Spot may have been around since long before the dawn of astronomy, and it looks like it will exist forever. But how can it live so long when the biggest storms on Earth last for only a few days? At the University of Washington in Seattle, Professor of Atmospheric Sciences Peter Rines thinks the answer lies in a bowl of water. A model of Jupiter's atmosphere, where he will attempt to create a great red spot.
Okay, take it up. Okay. Going to Jupiter, going to the outer planets, you've got gas atmospheres. They're doing almost the same things as a bowl of water spinning on this table. So we can actually build a planet or half a planet right here in the lab.
The first step is to get the right shape. A hemisphere, or half a planet.
Okay, let's go up to 3.4. Okay. See if we can make it more like Jupiter.
Jupiter spins 2.5 times faster than the Earth.
One of the remarkable things about this new substance you make when you take ordinary gases, ordinary waters, and spin them, is that they start organizing. And I think we've grown up in a world where moving your hand through a fluid makes just incredible chaos and complexity and little whirlies that you can't understand. If you go to this rotating world, this spinning fast world, you'll find that it's organized. There's order coming out of chaos.
The dye forms rings in the water, just like the rings around the planet. But they need to disturb it to try to make storms.
Just rotate a single fluid, tickle it with a wave maker. We see these shimmering waves move through the system. You see jet streams beginning to form up. We've got a piece of Jupiter just by doing that one thing. It's ultimate simplicity.
But there is no sign yet of a great red spot.
I wish we could
To solve the problem, Peter thought about why storms might exist in the first place and realized that Jupiter and the Earth have much in common. On Earth, the biggest storms we have are hurricanes, our closest equivalents to the Great Red Spot. A hurricane sucks up its energy from the warm ocean, enough to power winds of 150 miles an hour. But Peter thinks the biggest clue is that hurricanes always move from warmer to cooler areas of the Earth. He believes that storms on both Jupiter and Earth are doing exactly the same job, air conditioning the planets, regulating their temperature.
When you go to the fully featured planet, there has to be a source of energy, a fuel for all the motions you see. That fuel is heat. It's the heat of the sun, or it's the heat boiling up out of the core of the planet. What the storms do, they take the heat out of the hot zones to the cold regions. It's an air conditioning system, a gas conditioning system, which carries heat out of the tropics of the Earth or of Jupiter to the poles and then sends it out to space. In goes the North Pole.
The model is missing something. It needs a polar region made of crushed ice to create the temperature difference that Jupiter has and that its storms need.
Good hands.
We die for each other.
It's actually doing very well.
Suddenly, Peter's planet is teeming with storms, just like the surface of Jupiter. All the storms look very stable, but they can't all last forever. There is only one great red spot on Jupiter. Then Peter realized something amazing is happening. The storms are eating each other.
In a rapidly rotating planet like Jupiter, the eddies can't move north or south. They have to jostle each other like ball bearings in a raceway. They can increase their lifetime, grow older, last longer. They've lasted hundreds of years by competing with each other and actually gobbling each other up. The engine is turned up faster, and they compete for space, and one of them wins, and it lasts almost forever. And that's your great red spot.
The Great Red Spot is the solar system's greatest predator, a storm that eats hurricanes. It dominates Jupiter like no single storm has ever done on Earth, or any other planet we know of. Everything about it is extreme. A single storm big enough to swallow the Earth whole. A storm raging unchecked for over 300 years. But a storm that obeys the same laws as our own weather.
Jupiter is, in some ways, a simple model of Earth. I think ever since we had the really close encounters with Voyager flybys, and we had these stunning images of the red spot, the simplicity of it is wonderful and beautiful, and that many of us think that that's a piece of the Earth's action laid out before us.
By studying how this simple storm moves heat around Jupiter, we may learn how to predict the path of hurricanes on Earth, because the Great Red Spot is the most predictable storm there is, a monster that devours everything in its path.
How can we get a sense of Jupiter's Great Red Spot? The best way, I think, is to scale Jupiter down to the size of the Earth. Where does that put the Great Red Spot? It puts it in the Atlantic Ocean, exactly in a collision course with Miami, Florida. Leading it would be a terrific series of thunderstorms, just like a tropical depression or a tropical wave, the precursor to a hurricane.
It's time now for
the thunderstorms to the west of the Great Red Spot would even fool the experts.
No great shape to it yet, but it does have the elements for the beginnings of a hurricane. Of course, it is the season, so we'll
carreteras y avenidas principales debido a la evacuación en progreso. Esperen tráfico considerable.
This storm has all of the characteristics of a tropical storm that might be a hurricane. We get terrific rain, sheets of rain coming into Miami right now, thunder and lightning. The question is this going to form into a hurricane? You're looking for this telltale sign, an eye wall, spiral arms of a traditional hurricane. This thing that is out there, the Great Red Spot, is 1/3 the size of the Atlantic Ocean. You're looking right at it. You don't see it because it's too big.
And here's your weather update. Taking a look
Weather
at
forecasters would be expecting winds to pick up if a hurricane was coming. If this didn't happen, they would think the danger had passed.
Is a lack of wind activity. In fact, we haven't received any reports of winds over 10 miles per hour. So as we continue to monitor this storm as it moves toward the coast, we'll keep you informed. But as of yet, it does not seem.
If you look at the Great Red Spot on Jupiter, there's a beautiful clearing, a perfectly oval-shaped ellipse of clear sky all around the Great Red Spot. And that has just come overhead. And the false impression is the storm that could have been a terrific hurricane has not occurred. On its outside of this enormous storm is a jet of wind that is 300 miles an hour that goes all the way around it. And that jet is about to hit us. And there is no warning.
Low pressure system that we've been watching and waiting to develop into a hurricane simply never did. Of course, we did have some reports of some heavy rainfall, but never a hurricane.
The hurricane alert is over, but this is just the calm before the storm. The Great Red Spot is on its way.
If you know what's coming, then you want to run. But there is no way to know, because this is a storm that has never hit Miami before, and here it comes.
Only one thing can be predicted about hurricanes on Earth. Even the worst always run out of energy. In 1998, Hurricane Mitch struck Central America, the most devastating hurricane this century. By the time it blew itself out, it had devastated 6 countries, claiming the lives of 11,000 people and making 3 million homeless. Mitch found a way to be continually refueled. For almost a week, it came as close as possible to being the Earth's Great Red Spot. Having built up to Category 5, the most violent form of hurricane on Earth, it ran into the mountains of Honduras, and stalled. With most of its body over the warm ocean, it sucked in heat for days on end. After being battered by 180-mile-an-hour winds, this region suffered 25 inches of rain in just 6 hours. A deluge that washed away entire towns. But when Mitch drifted further overland, far from its source of life, the warm ocean, the storm itself began to die. Sooner or later, even our biggest hurricanes will hit dry land and run out of energy. But on the giant gas planets, storms are far more stable and more severe. Scientists believe Neptune storms, the great dark spots, last for years. Winds of 750 miles an hour have been measured on the planet Neptune. And the Hubble Space Telescope has captured clouds on Saturn moving at 1,000 miles an hour, the fastest wind speed on record. The weather on the outer planets of our solar system is relatively simple, because these planets are simple too. The Earth is more complex, the only planet to combine its thick atmosphere with oceans and dry land. A complexity that saves us. If they happen here, the colossal storms of the giant gas planets would hit land and die. But beyond the clouds, scientists are tracking a unique alien storm with the power to cross interplanetary space, a storm with tentacles that reach down to the surface of the Earth. This is weather driven by lethal radiation, space weather. Space weather is a torrent of high-energy particles drenching the atmospheres of all the planets, including our own. And it comes from the stormiest place in the solar system, the sun itself. Its only visible sign is the mysterious aurora borealis, the northern lights. But the aurora is the ultimate storm warning for every single human being on Earth. NASA scientist Bruce Surutani is watching for weather on the surface of the sun.
What most people see is a big yellow ball which gives us light, that gives us heat, that gives us sustaining life here on Earth. But the sun is the stormiest place in the solar system. The sun has an 11-year solar cycle, and at the peak of its solar cycle, there are lots of flares that come out 3 or 4 times a day. A solar flare is the biggest violent event that you can have in the solar system. It's 1 billion hydrogen bombs going off at once. It's absolutely enormous, something we can't even imagine.
When a solar storm erupts in a flare, 100 billion tons of high-energy particles can be set on a direct collision course with Earth, moving at speeds of 1 million miles an hour. The Earth's magnetic field funnels some of these particles into the polar regions, where individual particles collide with air molecules just 40 miles from the ground, producing the northern lights. The atmosphere is a vital last line of defense.
We're protected by the atmosphere, we're protected by the Earth's magnetic field. But once you venture out of that, once man starts to travel out of that, or even contemplate thinking, moving out of that, then these events are very important. The radiation from the particles can be harmful for both humans and for the equipment that they operate there in space.
17 Houston, you are go for orbit, go for orbit.
Those are kind words, Robert. We're go for orbit here.
By December 1972, the Apollo space program had put 10 men on the moon. But far beyond the protection of our atmosphere, every mission faced the terrible risk of a sudden and unpredictable rain of radiation from the sun. Apollo 17 was to be the most ambitious lunar landing ever. The astronauts would have 3 full days on the exposed lunar surface. But the mission faced an emergency that was not disclosed at the time, an emergency that would threaten the very lives of the astronauts. Gene Cernan was mission commander.
The sun is very prominent in space. Although you can't really look directly at the sun from the surface either, you can sort of glance by it without hurting your eyes. But in space, outside this atmosphere, that you just can't get your eyes anywhere near the sun. It's just brilliantly bright. It's almost piercing bright.
Solar storms happen at random. The biggest one ever recorded had erupted just 4 months previously, and no one could predict if another would follow.
We were aware that we were subject to some solar radiation, some solar flares. There was some activity between Apollo 16 and 17. We knew we were vulnerable to a whole host of problems we had no control over. Those we had control over, I'm going to tell you, I was arrogant to tell you that if that Saturn V guidance system failed on liftoff, I had the capability in my hands to fly that big old 38-story rocket ship to the moon. I would have done it. I trained to do it, I could have done it, and I almost dared it to fail. That's a certain amount of arrogance you have to have. But there's other conditions, other problems, whole host of problems that we're vulnerable to that we do not have control over.
Cernan and colleague Jack Schmidt worked at their experiments, unaware that a solar flare of unknown size had been reported to mission control.
They're expecting a little solar storm, and before the rain gets on the cosmic ray.
But when the crew were asked to protect a sensitive instrument used for detecting background radiation, Cernan knew that Houston had a problem.
We put it in a particular container to protect it. And a question I think Jack Schmidt asked at that time of the ground, well, what about us? You know, where do we go and what do we do? Well, he knew what the answer was as well as I did, and it would have been catastrophic.
Yeah, Jack, you're going to have to take the pan now.
No one knew if the solar flare would be followed by something even worse. The most dangerous form of space weather known to man, a coronal mass ejection. In the corona, the outer layer of the sun's atmosphere, massive energy is stored in giant loops, like twisted rubber bands. The stormy motion of the corona puts enormous strain on the twisting loops until eventually they snap. The massive explosion releases a storm of high-energy particles that could burn an astronaut alive.
The danger is these coronal mass ejections are moving very, very fast, about 1 million miles an hour. And as they travel through, they form a shock front in front of them. At this shock, there are electric fields generated that accelerate particles to very high energies. So essentially, a person in that type of environment is exposed to radiation, the same type of radiation that you get from atomic bombs and that sort of thing, that causes radiation sickness and, in severe cases, could cause death.
If a coronal mass ejection was heading towards them, the Apollo 17 astronauts would almost certainly die on the moon in a torrent of lethal particles.
We had no radiation protection for any major activity on the surface moon. We had nowhere to go. We had no cave to hide in. Spacecraft would have not protected us, and our suits certainly would have not protected us.
There was nothing the astronauts or mission control could do except wait to see if the storm would arrive. The crew of Apollo 17 escaped the moon unharmed. There was no coronal mass ejection. 4 months earlier, when a massive solar storm did take place, the crew would have died on the moon, with the whole world watching. And scientists now believe that unpredictable solar storms threaten not just astronauts, but the whole world. The air in our atmosphere only has the stopping power of 13 feet of concrete. And one day, there might be a solar storm powerful enough to batter a hole in this thin protective layer. At the Infrared Telescope Facility high on Hawaii, NASA's Jack Connerty sets his sights on the one place in the solar system that can show us what our world would become if our atmosphere failed us.
Yeah, that's nice. Here's the footprint right there. Can we bring up a similar image in the big window?
There you go.
Sweeping across the southern hemisphere of the giant planet Jupiter is the home of the most bizarre and deadly form of weather known to science. In 1998, the Galileo spacecraft sent back the first color image of an entire world consumed by the light of the aurora. A technicolor dream hiding a nightmare reality, or a vision of our own world stripped of its protection from space weather. Jupiter's moon, Io.
If you were standing on Io, down by the equator, you'd be bathed in this fantastic blue glow. You'd see maybe curtains of auroral emissions. You'd enjoy probably the greatest light show in the solar system, but only for an instant. The radiation would kill you.
Io's spectacular light show is visible evidence of the radioactive soup washing in its atmosphere. But there's a mystery. The same size as our own moon, Io should be too small to have an atmosphere. And with no atmosphere, there can be no aurora. The clues in this mystery include one of the most shocking discoveries in the history of space exploration. In the early morning sunrise, boiling hot sulfur dioxide gas rises 60 miles above Io's surface. In the vacuum of space, it freezes, falling back to the ground as extraordinary blue snow. An eruption of the Prometheus volcano, the first active volcano seen outside the Earth, named after the Greek hero who stole fire from the gods.
It turns out, now we know that Io is the most volcanic object in the solar system. It's almost a vision of hell. There are hundreds and hundreds of active volcanoes currently on Io.
But what scientists couldn't work out was how volcanoes made the aurora possible on Io. Even today, the release of gas from the Earth's volcanoes is constantly changing the composition of the air we breathe. This process played a major role in creating our atmosphere in the first place, more than 4 billion years ago. Was Io growing an atmosphere? There's only one place on Earth where the answer can be found: the dangerous slopes of an active volcano on the island of Hawaii. NASA volcanologist Rosalie Lopez has come to high altitude to look for the source of Io's atmosphere. At 11,000 feet, Mauna Loa is so remote that more people have walked on the moon than in this alien and forbidding landscape. It's also unique. Io's surface is coated in volcanic sulfur, and this is the only active sulfur flow on Earth. The closest Rosalie will ever come to an impossible dream: to work on the surface of Jupiter's moon.
Io is really a hellish place. But to a volcanologist, it's absolute paradise because of all these volcanoes erupting all over the place and these volcanic plumes erupting all over the surface. It's just absolutely fantastic. And if I could be sure that I would survive it, I'd go there in a heartbeat.
Rosalie and her colleagues have established Hawaii as a living Io laboratory, a testing ground for new theories. Volcanologists need to know how hot Io's volcanoes really are. They could be as hot as volcanoes on the molten Earth more than 4 billion years ago. Temperature measurements of Io from spacecraft have been inconclusive, but a thermal camera can be used to make a temperature model of similar lava flows on Hawaii. By working out how quickly lava cools down, Rosalie can calculate the true temperature of Io's lava when it first comes out of the ground.
Well, it's absolutely incredible. I've got the entire lobe as it comes out. 1, 2, 3, 4. 1, 2.
What we're learning is that the lavas on Io are indeed very hot temperatures of about 1500 Celsius, which are temperatures of ultramafic lavas, and these haven't erupted on Earth for a very long time.
Io's active volcanoes are giving scientists a new way to study a process that's long extinct on Earth. But can they be producing enough gas to create an atmosphere? The active Kilauea volcano releases a plume of sulfur dioxide, just like volcanoes on Io. It's poisonous, so Rosalie and her team must stay safely upwind, and that demands smart thinking.
You can't send aircraft flying through a volcanic plume. That is very, very dangerous. So we had this idea of flying a kite. And also a kite is cheap, is relatively expendable. And what we're trying to do is find out the distribution of temperatures and of particles and of gases inside the plume to model the physics of the plume and how the plumes erupt.
If they can work out how the gases are behaving once they leave the crater, they can apply their findings to the plumes they see on Io.
We see volcanic plumes on Io of several different types. We have plumes like the Prometheus plume, which have more particles in them, and Prometheus is always active. We call it the Old Faithful of Io. And some plumes that are almost pure gas. It's very difficult to image.
Okay, we're logging data. Oh, that's a perfect sample.
Through their study of Hawaii's volcanoes, Rosalie and her colleagues believe they have solved the mystery of Io's atmosphere.
One of the things that we found out is that the plumes create their own atmosphere, so the volcano on Io creates a local atmosphere around it, which can even produce what we call pyroclastic flows on Earth, which are flows where essentially part of the plume collapses and can move, hugging the ground.
They have found that a single volcano on Io can produce 10 tons of sulfur dioxide gas every second.
So the sulfur dioxide is coming out of the volcanoes, is producing a local atmosphere and also, we think, a more extended atmosphere all around the planet.
Io's atmosphere is 1,000 billion times thinner than the Earth's. Just enough to make it light up with the most incredible aurora in the solar system, but no protection against the lethal bombardment of high-energy particles. Without the Earth's gravity and our much thicker atmosphere, our own planet would be defenseless against a deadly rain from the sun. And suppose the sun erupted with an explosion of high-energy particles so vast that our atmosphere could not stop it, because no one yet knows what the sun is ultimately capable of. Years after the Apollo 17 crew escaped a solar flare, a new generation of NASA astronauts goes through training in Houston for missions to the International Space Station. Over 1,500 hours of spacewalks will be needed to build the space station. 1,500 hours of human exposure to the sun. Work is scheduled at times when protection from the Earth's magnetic field is greatest. But it's a near certainty that a major solar event will hit the station during its construction. To save themselves, they'll need warning of the coming storm. But right now, dangerous solar events can only be detected just 10 minutes before they reach the Earth. Research elsewhere has shown that solar storms threaten not just astronauts, but every human being on the planet. At high altitudes, where the atmosphere is thin, a transatlantic flight can expose passengers to the equivalent of a medical X-ray. Long-term exposure may create a leukemia risk for airline crews. And 6 times in the last 3 centuries, killer flu epidemics have stalked the Earth, claiming millions of lives in precisely the same years as maximum solar storm activity. Scientists have yet to explain why. So the race is on to forecast space weather, but this is a science in its infancy. NASA's Joe Davila compares it to our limited knowledge of the Earth's weather more than 100 years ago.
We had observations of the weather in various separate parts of the Earth, but we didn't have a comprehensive picture. And that's where we are with the sun. We have observations of the sun for the last 20 years, but we don't have a real good, long, continuous record that we can truly understand the basic physics that's going on.
4, 3, 2, 1.
White Sands Missile Range in New Mexico is one of the most secret research establishments in the world. Joe Davila is going in search of the ultimate alien storm. He's making last-minute preparations to fire a rocket at the sun.
We prepare all this stuff.
This is the sharp end of science, as solar exploration moves into the 21st century.
T-minus 20 minutes in counting. Operation Alpha Delta.
Joe Davila aims to go beyond the veil of the Earth's atmosphere. Like a weather forecaster watching for a hurricane, he's looking for early warning signs that might be the birth of a solar flare or a coronal mass ejection. This is $1 million mission, and the last chance for a decade to make it count. Every 11 years, the sun becomes significantly more active, and this is a solar maximum year. They set the controls for the heart of the sun.
There it is. It's up.
The tension mounts.
Darn thing gets colder.
I'm not sure why people take the scene, but they're seeing.
Davila knows that the onboard TV camera will capture not just cutting-edge science, but the ride of a lifetime.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Plus 15. Plus 20.
The square patch of white sand dunes near the missile range is clearly visible below. The rocket is already at an altitude of 80 miles. The surface of the sun emits ultraviolet light. Usually this would be absorbed by the atmosphere. But now the scientists have a clear view of the most violent storms in the solar system.
Okay, we should be acquiring any second now. Still don't see it. Here it comes. Here comes the sun. All right, it's coming in. Now it's going to the correct position. Okay, there we are. Camera's running. Start enable. Experiment start.
We know that energy comes from the surface of the sun. It comes from these convective motions that we see. The riddle we're really trying to solve is how does that happen? What is the exact mechanism of that? If we can understand that, then we can predict that. If we can predict how that's happening, we've taken a big step to predicting the space weather. The sun has been around for about 4 billion years now and has been operating in more or less the same way. Since the space age, we've learned that there is such a thing as space weather, that the sun influences the planets. And it's only been since we've had satellites and space probes that we've known that.
No, they buried it in the dirt right up to the door.
Okay.
Okay, look on this coax. Yeah, it's hot, isn't it? Ouch.
Just half an hour after liftoff, the rocket is safely back in Joe Davila's hands. The data gathered on this flight will be used to design a new generation of space weather satellites, an early warning system for astronauts and commercial airlines. But there is 100 years of catching up to do.
And this is a very difficult problem. It's a very complicated problem. If you look at the sun, it's a very complicated place. It's going to take many years to actually understand the physics of this. What we can hope to do within the next few years is develop a capability where we have enough observations where we have seen this type of event on the sun before. Therefore, we know its effects will be something like what we saw before. And I think that type of capability is something we can look for in the near term.
That's iron 14 334 and iron 15 335, so that's in there. Definitely see some structure in the lobes.
Well, I'm satisfied that we have data here. To understand how good it is, we need to do some processing on it. And that's going to take a couple of weeks. And I'm sure we hit the second target. I think running computer models to generate what the sun is going to look like 3 weeks from now is something that we would like to get to, but we're not going to get there for a while.
The sun is so unpredictable that some scientists believe the storm to end all storms is yet to come. Our star is 4.5 billion years old, but we have only been observing the storms on its surface for 2 decades. In search of more information, astronomers have found stars within our galaxy which are similar to the sun, but produce flares nearly 10 million times more powerful. A solar flare a fraction of this size would cause a catastrophe on the Earth. But there is no way of knowing if this has already happened in the distant past, or if it will happen again tomorrow.
We think that we know what the maximum flare intensity is for the sun, but it's possible that flares 100 times brighter have occurred in the past, and it would leave no trace in history.
If Bruce Suratani is right, a solar storm could totally destroy the ozone layer in the atmosphere And with no protection from the sun's ultraviolet rays, the food chain would collapse. He has come to Toronto, Canada, to envisage the end of the world.
If there were a flare 100 times or 1,000 times brighter than a typical flare that we see at the sun, it would cause a gigantic magnetic storm, something like we've never seen before. What you're first going to see is this bright aurora occurring in the poleward region, upward from Toronto. The magnetic field starting to get peeled away from the Earth. We're seeing brilliant auroras to the north. This aurora is coming down southward, coming toward the equator, coming toward Toronto.
The aurora borealis usually only happens in the far north. But this is a fireworks display that everyone on Earth is going to see.
Eventually, this aurora will be overhead, and you'll see the particles come down the lines of forest, and you'll see the bright colors. It'll be splashing down upon you.
The electronic control systems in orbiting satellites are being destroyed. Disabled satellites slow down and crash to Earth. The storm carries its own electromagnetic field. This induces a gigantic electric current in all power lines. The worst geomagnetic storm in history caused a total blackout in Quebec in 1989. But now the lights are going out all over North America, Western Europe, and the world. And the rising sun isn't finished. The storm has set up a chemical reaction in the atmosphere that will blast a fatal hole in our last line of defense.
The one protection we have on the Earth is the ozone in our atmosphere. It stops the ultraviolet from the sun, stops it at high altitude so it never gets down to the surface of the Earth. We think that now that the sun is coming up, that we're safe and everything is over. But one thing we've forgotten about is energetic particles would destroy the ozone in our atmosphere. And this will allow ultraviolet to come down to the surface of the Earth. With a giant flare happening at the sun, basically would have a mass extinction on the Earth.
The astronauts who one day travel to the planets will surely have to handle weather at its most extreme. Alien weather. The first humans on Mars will face dust storms that can engulf an entire planet. On Earth, these same storms are held in check by the water that Mars lost long ago. Our planet is a launching pad for the long journey into alien weather. But though our deserts may compare to Mars, a dust storm will never cover the world. The greatest storm of Jupiter will rage forever, a lord of the atmosphere with unstoppable power. Even as they destroy, The worst storms on Earth are dying. Cut off from its power source in the oceans, no hurricane will ever lay waste to continents or dominate the planet like the Great Red Spot. The Earth is a laboratory where we can study these storms in safety and be glad to never feel their fury. Only space weather can reach across the solar system, drenching entire worlds in deadly radiation. Worlds that are a vision of hell. But unless the sun explodes with the storm to end all storms, we will never experience hell on Earth. The atmosphere gives us shelter from our unpredictable star. So far, we have been lucky. The Earth is the only planet with water, dry land, and a dense atmosphere, the unique combination that gives us weather we can live in. Even at its worst, our weather will never wipe us from the face of the Earth. The Earth will never become planet storm. But if we journey to the planets, alien weather is lying in wait, and it's an awesome reminder that there is truly no place like home.